As another example, let's consider motion where x of t equals a times the cosine of pi over 4t and y of t equals a times the sine of pi over 4t. So that our r vector, and it's r of t, probably don't have room to write that here, I'm not going to try. It's xi plus yj, and getting the t dependence and everything explicit here, we see that that's well, the a cosine pi over 4t times the I vector plus a sine pi over 4t times the j vector. Now we can get our velocity and acceleration, and we'll do that in a minute. It's very easy to take that derivative, just know the chain rule and how to take a derivative of a sine or a cosine. But let's see what kind of path this gives us. Let's see what we can figure out about the path just from general knowledge. Okay, now you've had calculus. You should be fairly familiar with this idea. In any case, if we square x and square y and add them up, we're going to get a squared. Why is that? Because what we're going to have is we're going to have a squared times the cosine squared plus a squared times the sine squared. I don't have room here. To write this out in detail with all the functional dependencies, but it's a squared times the cosine squared of this plus a squared times the sine squared of the same thing, and we factor out the a squared and we get a squared times the cosine squared plus the sine squared of the same thing, and we know that's a Pythagorean identity, and that's 1, so we just get a squared. So there's a little blurb to say why, but it's just a Pythagorean identity, and that should be very straightforward. If it isn't, you want to lock that in. You're going to use that again and again. And that implies, of course, x squared plus y squared equals a squared. X squared plus y squared is the square of the distance of the xy point from the origin. So the distance, the square of the distance from the origin is equal to the square of a, which means the distance of xy from the origin is a, meaning you have a circular path of radius a centered at the origin. Another aspect of this motion, you know that the cosine and sine are periodic. Every time the argument of the function changes by 2 pi, the function goes back to where it started from. So both the sine and cosine have that property. So when pi for 4t changes by 2 pi, you complete motion around the entire circle. Now you should probably draw that out and work out the details of it. It's very important. Okay, so when pi over 4t changes by 2 pi, well, pi over 4t changes by 2 pi when t changes by 8. Okay, you could just let pi over 4 times the delta t equal 2 pi and solve for the delta t. You would get 4 over pi times 2 pi, which is going to be 8. And that's going to be the delta t that's required to move you completely around the circle back to your original point. So the path is completed with a period of a. The circular path is completed with a period, I think I said a, 8. Getting close to dinner. Okay. Now, let's go back up here. We know this now. We know, and we could draw a picture. We have a circle of radius a, and we have a particle moving around that circle. Delta t for 1 revolution, let's say. Revolution isn't quite the right word to use here, but I'm going to fudge and use it. Okay, now the period of motion around this circle is 8. Okay, well, let's calculate the velocity and acceleration vectors. Now let's think about it though for a minute. We have a particle moving around, or a point moving around this circle. What's its velocity? Well, its velocity at every point is going to be tangent to the circle, so at any point we want to draw a velocity, we're going to draw a vector tangent to the circle. Now what about the acceleration? Well, the vector is changing. It's changing in, I'd have to draw it. Turns out it's centripetal, and we can draw that. We just get an isosceles triangle that shrinks down to 0, and the change in the velocity is always then perpendicular to the velocity, or the change in velocity approaches perpendicular to velocity as the increment approaches 0. You're not going to understand what I said unless you already understand it, but there's an easy way to do that. It's going to turn out that our acceleration vector is toward the center. Now we're going to get that by taking the derivatives, and we can also get that geometrically, and we want to do it both ways. So we are going to do that. We're going to do the thing I'm talking about here that I was just talking about, but we'll do it in detail with a bigger picture so we can see it. Okay, so velocity is dr dt. Well, it's easy to take that derivative. And if you don't know why the derivative is what I'm going to write down, because I'm not going to explain it to you, you need to dig it out. You need to go back and review the chain rule and the derivatives of the sine and cosine function. But anyhow, the derivative is going to be negative pi over 4a times the sine of pi over 4t times I plus pi over 4a times the cosine of pi over 4t times j. And that's, again, very straightforward. That's just very basic derivatives and not a very sophisticated application. The acceleration is dv dt, so we have to take the derivative of this, which is going to give us negative pi squared over 16a cosine of pi over 4t I minus pi squared over 16a sine pi over 4t times j. No mystery here. We can factor out the negative pi squared over 16 times. Let's just factor out the negative pi squared over 16. You'll see why in a second. Okay, that's going to be I'm not going to read it to you. You'll understand this. I'm going to put another set of parentheses here so I can make this plus a sine pi over 4t times j, close the parentheses. Now look at this. Pause the video for a second and look at this and see if you see anything like this anywhere else. And I guess I got carried away with parentheses there. Okay, well, if you looked, and if you haven't seen it, look again. This is the same as this. So this is negative pi squared over 16 times r of t. Now the pi over 4 is going to carry units. It's going to carry units of radians per unit of time, units of angle per unit of time standard. When we're in radians, we're dealing in radians if we don't have any conversion factors. So we do calculus always with angles in radians. So pi over 4 is going to actually have units of radians per second. So when we multiply it by t, we get units of radians, so we can take the cosine of the angle. So that pi squared over 16 is actually going to have units of radians squared per second squared. And the whole point of that, you don't have to know all that. Just write down the units whenever you do anything, and they'll come out. This a vector is on a different scale than the v vector or the r vector. The scales are not commensurate. Now, I'll come back to the reason for that. I said that, but we see that the a vector is a negative multiple of the r vector. Okay? Now, what's that mean? Well, what's the R vector for this point? The R vector goes from the origin out to this point. So what's the direction of the A vector going to be? Well, it's a negative multiple of the R vector, so the A vector is going right back toward the origin. I don't have to draw it big. Pi squared over 16 is less than 1, so we could get away with that, but the number doesn't matter. We don't know what the scale of the acceleration is, but it's going to be this. Okay? The other thing is the magnitude of the R vector is always A, so that the acceleration vector always has constant value. So the acceleration is constant as the particle moves around the circle, and it's back toward the center, which is why we call it centripetal. Centripetal means toward the center. I think I don't know Latin that well. Okay. Another thing we see is that the velocity vector is perpendicular to the R vector. Now, we know that because the R vector goes from the center to the circle, and the velocity vector is tangent to the circle, so we have a simple geometric argument. A tangent to a circle is always perpendicular to a radial line, and the R vector is a radial line, or constitutes a radial vector at least. Okay? And we can also verify that. R is perpendicular to V because a radial line is perpendicular to tangent. And also, R is perpendicular to V since R dot V equals 0. And you can, here's your V vector, here's your R vector. I'd factor out the A, and I'd factor out the negative pi over 4A in this one, so that you just have the negative pi over 4A squared multiplied by cosine of this thing times I, plus the sine of this thing times J, and here you're going to have a negative sine of this thing times I, plus the cosine of this thing times J, and just do what I say, write it out. In writing it out, you'll see it, and you need to write it out. You need to write it on a piece of paper so that you really see it. That gets it in your brain. I think neuroscience is beginning to get to the point that it realizes everything I've known all my life. And of course, I haven't known much. But that activity stimulates brain pathways, reinforces brain pathways that are very important for understanding what's going on here. Okay. So you do the R dot V, you're going to get 0, and that proves that R is perpendicular to V, which you knew anyway from the geometry. Okay, we'll continue with this analysis.